Hello guys, welcome to my channel. This is Ehsan, and in today's video we're going to talk about common source amplifier. In this amplifier, the input signal applied into the gate and the output is getting out of drain of this device. We're going to talk about this amplifier. We're going to calculate the gain of this amplifier and how we can extract it from the small signal model, and after that I'm going to give you some good example of how you can calculate the gain by just inspection, and this is important, and how we can apply it to another common source amplifiers as well, just by seeing the resistance in different nodes of this amplifier. And then I'm going to calculate the condition about how this transistor work in saturation, because this is the assumption that we have to make in order to this transistor works as an amplifier. But before we get started, if you're new here, please give me a thumbs up, hit that subscribe button, and also the notification bell, so whenever I upload a new video you'll be aware of it. Let's jump into it. This is a common source amplifier, and if you already seen my videos on a small signal model, we can draw a small signal model in order to calculate the gain of this amplifier. So this is the small signal model. This is gate, source, VGS, and this is a drain current of GM-VGS. This is source, this is gate, and this is drain. Now I'm gonna add the parameters of this circuit. This is input Vin, which is applied to the gate of this device. So this is Vin, and you have to assume that this is an AC voltage, because we're going to calculate the gain, and you have to assume that the device already had a DC bias, and which can operate in saturation. So what is source? Source is connected to the ground. This is source. And how about the drain? This is drain. Drain is output voltage, V out, and drain is connected to RD. This is RD, and after that it is connected to VDD, and this is VDD. Is this the correct model for this amplifier? Just take a look at it. I'm gonna make you to be an active audience. Just let me in the comment section what is wrong with this model. There is some problem with this. This is a small signal model. So in a small signal models, you have to be aware that you had to eliminate the DC voltages or DC currents of the device. So you had to short circuit the DC voltage and open circuit the current source. So for this VDD, you had to eliminate it and just connect it to the ground. This is important because this is an AC model, and we're going to calculate the gain of this device by this model. So the only parameter that you had to take care of it is VGS, and this is a really simple example, because in this situation VGS is equal to Vin. So VGS equals to Vin. Now in the output I can write it down like this. Instead of GM-VGS, I can write it GM-Vin. This is going to make it so much easier to calculate, because I'm looking for AV. What is AV? Small signal gain, V out divided by V in. So I'm looking for V out and V in, not the other parameters. I'm going to use KCL in the output node. KCL at V out. So this is the current through RD, V out divided by R out, plus this is another current which is equal to GM times V in, equals to 0. And by really simple mathematics, you can get the result that V out divided by R out equals to minus GM times V in. Now I can calculate the gain, which is V out divided by V in is equals to minus GM times R out. So this is the gain of this amplifier, GM R out, by neglecting the channel length modulation, because there is no early effect or channel length modulation, so I neglect the resistance between drain and source. Don't worry about it. I add it in just a matter of seconds later. But look at this formula for this amplifier, minus GMR out. This negative sign said that there is an 180 degrees phase difference between drain and gate of this amplifier, and GM is dependent on the current of this device, and R out here is R out. I'm sorry, I'm using R out, but this is R drain, not R out, RD. This is RD. So I had to correct this mistake. Sorry about that. This is RD. Okay? This is RD. This is the gain of this device. Now I'm going to consider this circuit again, and I'm going to give you an important tips from the Razavi's book in order to just look at this circuit and set what is the gain of this amplifier. And by using this method, you can set the amplifiers with this structure just by inspection. But you had to be master in using this technique to look at the different nodes of the amplifier and set what is the resistance seen from that node. And I'm gonna create different videos for just this resistance. So again, this is our amplifier, our drain. This is the MOSFET transistor, for example M1, and this is V in, and this is VDD. So as I told you, the gain voltage of this device, which is V out divided by V in, equals to minus GM times RD. No problem with the negative sign, but let me just write it down as something like this. Negative, this is a fraction division sign. Let me just put RD in here and put 1 divided by GM in the denominator. Okay, why am I doing this? So I'm going to draw a new formula, and this is V out. If you're looking at the drain of this device, because this is the output of this amplifier, and we're going to call this R out. What is the R out seen at the drain of this device? By neglecting the channel length modulation, you can only see RD. So R out, which is the resistance seen at the drain of common source amplifier, you can put it in the denominator for this amplifier, divided by this resistance seen from the source of this amplifier through the gate, and you can only set this when you want to calculate the resistance. You have to assume that the another voltage or current devices are just eliminated, which means that when I'm going to calculate this resistance, let's just call this Rx for the sake of simplicity. Okay, this is Rx here on the denominator. You had to assume that the V in is connected to the ground. Okay, so here is AV, negative sign. What is R out in this device? R out in this device is going to be RD, just RD. And what is the Rx? Rx is the resistance seen from source through the gate of this amplifier when V in is connected to the ground. Let me just calculate this because this is really important. This is the small signal model, plus minus VGS. Here this is GM VGS, and this is RD, which is not important in this calculation. And this is V in. Okay, this is V in. I'm gonna look at this amplifier from the source in order to calculate Rx. How can I do that? I had to put a voltage test, which I'm gonna call this just Vx, and calculate the current Ix. In other words, I'm going to calculate the Vx divided by Ix in order to calculate Rx in this simple model. But just consider this: the input voltage had to be grounded, so this one is connected to the ground. Be careful with that. So this is an important assumption that you had to make. Now I'm going to calculate Vx divided by Ix. What is Ix? Ix is really simple. This is Ix and this is GMVGS. By using KCL in this node, you can set that Ix plus GMVGS equals to 0. So you can calculate VGS in this formula. VGS equals to minus Ix divided by GM. Now, by using KVL in this loop, you can calculate the relationship between Vx and VGS. You see, starting from here, minus Vx minus VGS equals to 0. So VGS equals to minus Vx. As you can see, by using these two formulas and substituting VGS with minus Vx in this formula, you can set that minus Vx equals to minus Ix divided by GM. So what is Vx divided by Ix, which is Rx, equals to 1 divided by GM. This is an important formula, and you have to keep that in your mind when you look at the transistor from the source of the device. In order to calculate the resistance, this resistance equals to 1 divided by GM. So this is the gain for this amplifier, and this is how I'm going to calculate this. Now imagine this: I'm going to calculate the gain of this amplifier when I have an early effect. So again, negative sign. What is R out in this scenario? Well, here again I have RD, but in this scenario this is an R drain source of the device between drain and source of this device. Here I'm gonna draw it carefully. Just eliminate M1, and this is the resistance between drain and source, which I call it R drain source, when I consider the early effect. So what is this R drain source with respect to RD? One node is connected to each other, and the other node, what about the other node? This is grounded, but this is virtually grounded in a small signal parameter. As I told you already, the independent sources had to be short circuited and eliminated. Actually, the voltage dependent sources had to be short circuit, and the current independent sources had to be open circuit. Okay, so here we have R drain source parallel with RD. So parallel with R drain source. How about the denominator? The denominator is still the same, because I'm seeing it source of the device through the gate with V in short circuiting. So this is again 1 divided by GM. As you see, this last formula, which is this one, this is some kind of generalization. I try to come up with these new formulas, and my reference is Razavi's book. Razavi is really great in this, in teaching this method. It's really great idea, because you just look at the circuit and said what is the gain. And why I use this proof in here? This proof is helping you in order to understand better. It is really important to learn this by proof, not just by seeing this circuit and this is that and that's that. You have to know this. And another important point I'm gonna add at the end of this video, this is about the condition that this circuit had to have in order to work in saturation. Because when we want to calculate the amplifier gain of this device, we have to aware that the DC bias is okay and the transistor works in saturation. The first assumption is that, let me just somehow make it a better real example, because when I write it as a V in, it doesn't imply everything. V in, I can separate it into two different sources. There is plus minus VGS of this device as a DC bias for this device to operate it in saturation, and there is a small signal parameter V in. Okay, this is the real concept of V in here. Now I'm going to calculate the operation, the condition for operation of this device in saturation. This means that I use my formulas in DC, not in AC. So just for the sake of simplicity, now I'm gonna eliminate this V in and short circuit it. This is the DC bias, and I consider that the first condition here is that the DC voltage, which is VGS of this device, VGS of M1, which I'm calling VGS1, had to be greater than threshold of this transistor. This is the condition for this transistor M1 to be on. And how about the saturation? The saturation is this one. Condition for saturation is this one. The gate drain of this device had to be less than V threshold in order to this transistor to work in saturation. So what is the gate of this device? The gate is VGS minus the drain voltage. Here, this is the drain voltage of this device. And if you all remember, this is the drain current And in order to calculate the drain voltage, you had to use your KVL here, and the drop voltage, this is VDD, and the drop voltage over across our drain. So the drain voltage is going to be VDD minus RD ID. This had to be less than threshold voltage of this device. With this formula, I can set that just using some mathematics, VGS minus VDD plus RD ID less than V threshold. I can now calculate the RD ID condition for this device, which is less than, had to be less than VDD, and this VGS is going to be negative on the right hand side minus VGS plus V threshold. This is the condition for this circuit to work in saturation, because most of the times you had to check this in order to design your parameters. For example, design your W over L of this transistor, or design your R drain. This is the condition that you had to be aware of it and take care of it to work in saturation. I try to use some examples to get you familiarized with the design process of this amplifier. Okay guys, I hope you liked this video. If that's the case, please give me a thumbs up and share this video with your friend. And I'll see you in the next video. Thanks for watching.